Hi everybody, this is Maria Thomas with one more organic chemistry video. We'll be looking at enolates today and taking a look at different reactions that involve them, how to make them, how they react, and some general examples. So I guess the first question is, how do you make an enolate? Well, first of all, this is the structure of an enolate. It has a negative charge on the oxygen and a double bond between the two carbons next to it. So in order to make this, a base has to come and actually grab a proton. But it can only grab a very specific alpha hydrogen. So not this one over here, but this hydrogen that's actually on the alpha carbon. The alpha carbon is the carbon that's next to the carbonyl group. So now we can show the base grabbing that, pushing this up and up again to form the enolate. Now this enolate formation could either be reversible, like in this reaction, using a base such as NaOH, NaOET, etc. Or it could be irreversible using a base like LDA or NaH. So now I guess the next question is, how do these guys react? So if you'll notice, there's a couple of areas of high electron density here and here. So they actually react in this way, pushing this down, pushing this off. So remember, this was your area of high electron density, and it has to attack an area of low electron density, which could be a carbonyl carbon like this, or this carbon next to a halogen, etc. But wait a second, didn't we talk about reversible and irreversible enolate formation? How does that work? So let's start with reversible. And here's the example reaction we talked about. So let's say you have this big beaker where this reaction is happening. You have a bunch of base molecules in there, and you also have your original reactant still present, as well as your enolate. So remember, this is a reversible reaction, which means you've got equilibrium arrows, which means a lot of these and a lot of these guys are still present inside the beaker, even after the reaction is over. And here's a few more of them floating around inside the solution. So we said that enolates like to react with areas of low electron density like a carbonyl carbon, right? But hold on, these molecules, these original molecules that are still floating around in the solution, actually have a carbonyl group that the enolates can attack. So they can do this and go ahead and actually attack one of their previous forms. And I've gone ahead and drawn this a little more clearly in the next page. And this would give you this product, and I've gone ahead and drawn the carbon numbers, and then you can actually protonate that oxygen using a water to form this structure, and this reaction is actually called an aldol reaction. And now if and only if you have heat present, which is shown with a delta symbol, you can actually go one step further. If you notice, you have another alpha hydrogen here, and that can be taken off by a base to form another enolate. Now that other enolate can actually react again by pushing its electrons down, but it can actually kick off this leaving group and give you this final product. And this step is actually called aldol condensation or dehydration. And actually, if you notice, using your heat, you pretty much took a water out. You took out one H here and one OH here. But what about irreversible enolate formation? Well, here's the same mechanism again, except that instead of sodium hydroxide, I've used sodium hydride, which makes the reaction irreversible because you form hydrogen gas, which sort of leaves the beaker. So that means that in your big beaker this time, once you're done with this part of the reaction, the only thing you have remaining are a bunch of these enolate molecules, since, all of your initial product got used up and even the hydrogen floated out. So now these guys need an area of low electron density to react with. So you could add something new to the beaker. You could add another carbonyl group, but we just talked about aldol reactions, so I'm not going to repeat that again. But you could also, pour in some sort of alkyl halide into the reaction, into the beaker, which means that the enolate could actually react with that carbon, with that alkyl halide, and I've drawn the product of that step in the next page. And the product would be this, and I've sort of gone ahead and drawn the carbon numbers for you for some clarity. And just so you know, this reaction is called enolate alkylation because you're essentially adding an alkyl group onto the enolate. So let's do a quick review of the enolates that we talked about today. They're formed when a base comes along and grabs its alpha hydrogen, pushing these electrons up like this, giving you your enolate. And the way these enolates like to attack is by using their area of high electron density, pushing these electrons down, and using this double bond to go attack something. Possibly an area of low electron density like a carbonyl carbon on this carbon, or onto an alkyl halide over here. Now, if the base you used was something like NaOH or NaOET, this enolate formation would actually be reversible. You would use equilibrium arrows, which means that both the enolate as well as the original reactant with the carbonyl are both present in the solution. And since enolates like to react with carbonyls, this newly formed enolate could go back and react with its old form to lead to the steps that form an aldol type reaction. Now instead, let's say you used a base like LDA or sodium hydride, which form an irreversible enolate. That means the enolate is the only thing you have left in solution. This original carbonyl is no longer present. So now you could choose to react it with some other carbonyl compound of your choice and do another aldol type reaction, or you could react it with some sort of alkyl halide to do an enolate alkylation reaction. And that's it. These are some of the big tips I had for you guys about enolate reactions, and I hope this video was useful for you. Thank you.